The next example that we can consider for our topographical map and level curves is we'll look at the function w, say, is our output, is equal to sine of pi over 2 times x squared minus y squared. To find the level curves, the topographical curves, we fix w equal to c, which gives us the equation that our function, this is our function in this case, is sine of pi over 2 times x squared minus y squared. And if that is fixed at some c value, then we can actually solve for c. Right? This is going to be, or I should say, solve for x squared minus y squared here. Think of the shape of these level curves. If we take the inverse sine function, arc sine of both sides, we get pi over 2 times x squared minus y squared is equal to arc sine of c, which gives us the equation x squared minus y squared is equal to 2 over pi times arc sine of c. And this is the algebraic equation of the level curves for this function, which means for various values of c in the range of this function, we have the level curves are given by curves of the form x squared minus y squared is equal to some k value, where this k is 2 over pi times the arc sine of c. So curves of this form are hyperbolas, like we talked about before. And so what that means is that the level curves of this function are exactly going to be hyperbolas. For various values of c. And specifically, they're going to be changing with the value of c that the function is. So these curves, these level curves, are giving us the value of the function, the c value of the function, for every single possible value of c. So again, if we open up a plotting window to try and visualize this, we can do just that. And so here we see a plot of the function in this example. It's the function is sine of pi over 2 times x squared minus y squared. And you can very clearly see that there at z equals 0, that's this light gray plane that's plotted. If we kind of rotate the plot a little bit, we're seeing that at z equals 0, the level curves, or the intersection of this plane with the surface, are exactly hyperbolas, as we predicted. And not only that, but if we want to make a plane down here, at the very bottom of the range, which is at -1, c equals -1, you can actually pick any value from -1 to +1, the range of the function, and do a cut of this function to get level curves. So let's say we stop here at c equals 0.5. Even at c equals 0.5, right, we're getting level curves that are exactly hyperbolas, which is very cool. Now, I do want to note that the plotting capabilities of certain plotting programs for various multivariable functions are going to struggle a little bit whenever you have very fast variability of the function. That's what's kind of happening here, in here as well. So even if we were to say zoom out a little bit, GeoGebra does its best to plot the function, but because there's so much variability, it's kind of very hard to plot the function out where it's changing very rapidly. That being said, we're very clearly seeing a picture of what we expected. But Desmos will give you a slightly nicer plot of just the curves themselves, the level curves themselves, if you kind of go through. And you can also do a slider. You can do a slider in both GeoGebra and in Desmos. But if we do sine of pi over 2 times x squared minus y squared equals c, and we'll go from -1 to 1, because that's the range of this function. You can see a clear plot of the level curves of this function. And the level curves of this function are exactly hyperbolas. And as you move along, around to the level curves are changing on these hyperbolas. So for instance, these curves are the level curves for c equals -0.5. You change c to 0.2, the level curves change. So these right here are the level curves for c equals 0.02. But the idea is that this is how we visualize these functions of two variables. And you'll notice that this visualization is only, we're visualizing a function of two variables inside the two-dimensional space that you're in. So this is a very, very useful tool for us in terms of helping us figure out what a function of 2D is looking like inside its domain space. So a natural question to ask is, can we extend this idea to functions of three variables? And the answer is exactly yes, we can. Specifically, this is done using what's called a level surface. Level surface is like a level curve, but for a function of three variables. Specifically, if we have a function of three variables, f of x, y, z, you say that the level surface of this function of three variables is what happens when, so the output is w and the function is a function of three variables, f of x, y, z. The level surface is what you get when you fix w equal to c for some fixed c value, and you consider the set of points x, y, and z that satisfies f of x, y, z is equal to c. The set of all points that satisfies this relationship the set of all points x, y, z that satisfies f of x, y, z equals c is called the level surface of the function f corresponding to the value c. So there are a number of different examples that we can go over of a function like this, or a level surface for a function like this. But I'll do a similar one to before, where f of x, y, z is equal to, we'll say, e to the negative x squared minus y squared minus z squared. The level surface for this function is going to be the following. It's going to be, well, we fix w equal to c, and we get that e to the negative x squared plus y squared plus z squared is equal to c. So we can take the natural log of both sides. And so we have then that x squared plus y squared plus z squared is equal to negative natural log of c. If you remember that x squared plus y squared plus z squared is rho squared, or the distance from the origin squared. That means that the level surfaces for this function of three variables are going to be spheres of radius rho, all given by having the square root of negative natural log of c exists. So this expression gives you the range of the function. You can do it using exactly the same calculation that we did before. But if we open up Python now and show a visualization using my plotting program for 3D functions, we can see a direct visualization of this. So this right here is the output of the Python graphing program that I wrote in Python, my custom Python code. And you can see that if we rotate this around, this is exactly a picture of this function, e to the negative x squared plus y squared. So you see that the level curves are definitely spherical. If you fix any value of the function, you get a sphere around the origin for that value of the function. The maximum value of the function is 1 right here. And I haven't plotted all points because the domain of the function is all values of x, y, and z. But as you move away from the origin, the value is getting closer and closer and closer to 0 at the minimum value of the function. So this is a pretty cool thing. These level surfaces allow us to visualize and understand how a function of three variables is changing with respect to moving around in space, which is a very important thing for things like temperature, mass density, really, the electromagnetic field, really any physical example you could think of, really is a function of variables, three variables in space, and possibly more variables like time. It could also be changing with respect to time. Let's do one more example. Maybe we'll do two more examples. We'll see. We'll do f of x, y, z is equal to cosine of pi times the square root of x squared plus y squared plus z squared minus 1. So to find the level surfaces, we fix w equals c, and then we look at the equation that we have here, which is cosine of pi times the square root of x squared plus y squared plus z squared minus 1. equals this fixed value of c. And if we kind of try to simplify this a little bit, we take the arc cosine of both sides to get pi times the square root of x squared plus y squared plus z squared minus 1 is equal to arc cosine or inverse cosine of c. We divide by pi and square both sides to get that x squared plus y squared plus z squared minus 1 is equal to 1 over pi times arc cosine of c squared. And lastly, if I add 1 to both sides, I have x squared plus y squared plus z squared is equal to 1 plus 1 over pi arc cosine of c squared. Remember, x squared plus y squared plus z squared is equal to rho squared. So what this means is that the level surfaces of this function are spheres of radius rho is equal to the square root of 1 plus 1 over pi arc cosine of c squared. That's what the level surfaces are. They're spheres of these varying radii. So you can use Desmos to plot this out if you want to see what these level surfaces look like. But I'm just going to open up my Python plot and change the function to this function so we can kind of see what this looks like. So this is the Python output for this function. And it's a little bit unclear at first, but if we kind of rotate this plot around a little bit, we can see that this is exactly what we have, that there's level surfaces here that are spheres. So the spheres are the constant levels, and as we move away, we're getting like a cosine behavior where we're close to 1, and we move away a little bit, and we're close to -1, and so on and so forth, going up and down on spheres. So it's a little bit harder to see with this random grid. We can go through and do it on an even grid and things look a little bit nicer. The random grid also looks a little bit nicer if you play around with the alpha setting of the points. But the main idea here is that on spheres of radius rho, where rho is this function of c, the value of the function is c. So we expect that the function is constant on these spheres, and sure enough, this is what we see. So in the next visualization that I'm going to show, x is from -L to L, y is from -L to L, and z is from -L to L. And sure enough, when L is 0.7, this is just from -0.7 to +0.7 in every direction. Obviously, the domain of this function is every point outside of the sphere of radius 1, which is this gray sphere that I plotted right here. And the function appears to be increasing and then decreasing. So it's basically decreasing. And the function appears to be decreasing. It starts at this value 1 right here on the sphere, which we expect the sine function when its argument is 0 to start at. And then it decreases all the way to -1. And then if we kind of zoom out a little bit, so this is now from -1 to 1 in x, y, and z, we see sure enough that it starts here on the sphere at 1, and then it decreases down to -1, and then it starts to increase again, and it appears to be spherically symmetric. So if we increase L equals 1.5 and 2.0, we see sure enough that's what's going on. And now we can't see the inside of the sphere anymore, but the inside of the sphere is still red at 1, and it increases or decreases until it goes out to -1, and then it starts increasing again. Same thing here, right? But only now we're seeing that on this larger sphere, the function repeats itself again. And all of these images right here are evidence of this fact. They're just kind of like progressively larger and larger and larger squares, so you can see that there really is this spherical symmetry with this function. So the case in point here, the point of all this is to show that even in 3D, the function behavior very heavily depends on the level surfaces. And sure enough, this function, as we increase from that sphere that bounds the boundary of the domain of this function, it's just increasing, decreasing, increasing, decreasing, just like we would expect for a sine function. Right? So it started to get a little bit blurry here at L equals 4.5, so I just doubled the number of points that I was plotting when I got to L equals 5 to really clearly show the behavior of this function. It's acting like a sine function, -1 to 1, -1 to 1, but it's a sine function that's depending on the radius of the sphere or how far away you are from the origin. So I thought this is a very cool example to show. And I'm going to end the lecture here. You can do many other examples, and I can definitely talk about more examples in the future, but this will end the lecture for today because I've described the concept of a trace, and I've also went over level curves for functions of 2 variables and level surfaces for functions of 3 variables. So I hope you all have a great day today, and I hope you learned something. But have a great day, and I'll see you next lecture.